How to go to space. We launch things into space by putting them on rockets with enough fuel called propellant to boost them above the Earth's atmosphere. Once the rocket reaches the right distance from Earth, it releases the satellite or spacecraft. To achieve this, the first step is to reach escape velocity, which is the speed needed for a free, non-propelled object to escape from the gravitational influence of a primary body, thus reaching an infinite distance from it. Escape velocity is about 11.2 km per second, and that's approximately 33 times the speed of sound. Why would you want to go to space? In the words of Walter Kugnor, Vice President of Exploration and Science Domain at Thales Alenia Space, if we take the risk of venturing beyond our terrestrial home, it's also to learn more about ourselves and our planet, improve life on Earth, and maybe, just maybe, find or create a new future for our children.
Weather balloons are used by scientists to measure pressure, temperature and humidity so that they can predict the weather of a location days and weeks in advance. The balloon is typically filled with helium as it is less dense in the atmosphere, so that it rises through the Earth's atmosphere, and as it does so, the temperature increases. This causes the helium to expand, making the balloon even less dense. Balloons can also be filled with hydrogen, which is cheaper and easier to manufacture. Hydrogen is used by many meteorological organisations, however, it is far more dangerous to work with than helium, as it is highly flammable. A weather balloon typically reaches an altitude of around 24 miles or 39 kilometres. This is because the balloon can only reach a height where the atmosphere surrounding the balloon has the same weight. The first weather balloon launch was in 1896 by Leon Tesserance de Bort, whose work contributed greatly to the discovery of the tropopause and stratosphere. However, scientists were unable to get the balloon out of the Earth's atmosphere and into space. The descent of the balloons was due to the temperature cooling in the evening, leading to the gases cooling and the balloons deflating into their descent. However, no control over the balloons descending back to Earth existed, so sometimes they would drift hundreds of miles, which would make data gathering very difficult. It took until 1955 for scientists to find a way of using high-altitude weather balloons to get into space. It is also worth noting that weather balloons were used in the 1990s by Alfred Wegener, which led to the discovery of continental drift. One case study of weather balloons being used to get into space is the Rockoon. This involves a high-altitude balloon carrying a small rocket. The rocket is ignited once the balloon fails to rise any further, so that its initial location is closer to space. However, a less powerful rocket is required than that of a land rocket, as the atmosphere means that it's less effect of gravity, for which the rocket must overcome. This leads to an easier flight for the rocket. The flight path of the Rockoon, however, can be unpredictable, so the rocket can be fired in the wrong direction. The rocket can be used to gather data remotely, but does not have a method of getting back into the Earth's atmosphere, so it will remain travelling in space as debris.
Let's have a look at the evolution of space rockets in the space race. It begins in 1903 when Konstantin Tsiolkovsky, a Russian high school maths teacher, published the first version of what is now known as the rocket equation. A crucial discovery was that the relationship between fuel and speed is exponential. If you want to double the velocity of the rocket, just adding twice as much fuel won't work. Post-war, the States began testing a staged rocket design, which has written the path of how rockets get into orbit and beyond today. October 1957 saw the famous Russian two-stage R-7 put the first man-made satellite into space, Sputnik. Soon after, the USA replied by putting their first satellite into orbit in Jan 1958. President Eisenhower then signed the NASA Act to catch up with the Soviets and massively increase state funding towards space exploration. In the race to be the first to the moon in September 1959, the Soviets crashed the first spacecraft on the surface of the moon using the Luna 2 rocket. And then it was in the 60s that the Earth was graced with this speech by John F. Kennedy.
The eyes of the world Now look into space, to the moon, and to the planets beyond. Our leadership in science and industry, our hopes for peace and security, our obligations to ourselves as well as others, all require us to make this effort, to solve these mysteries, to solve them for the good of all men. There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to us all. Its conquest deserves the best of all mankind. We choose to go to the moon. We choose to go to the moon.
Shortly before that speech in 1961, the Soviet Union continued to lead the race by making Yuri Gagarin the first astronaut on board a modified R-7 rocket with a flight time of 108 minutes and one orbit. In 1969, the three-stage, 2.8 million kilogram Saturn V carried mankind all the way to the moon, burning a casual 20 tons of fuel per second. Now, the space race turns to a new era, a commercial era, with companies such as SpaceX driven by the profit motive and reduction in cost of getting to space, inventing a radical new designs such as the reusable Falcon 9 rockets. The Falcon 9 has got to space 185 times and put more than 3,000 Starlink satellites above your heads. With a height of 70 metres, weighing in at just under 600 tonnes and able to carry 22 tonnes of payload into space each launch, the Falcon 9 is a two-stage rocket. It uses liquid oxygen kerosene propellant that feeds into 9 Merlin engines. Producing 1.7 million pounds of thrust requires more than 75% of its weight to be fuel on launch. After launch, the first major hurdle is max Q. At this point, the rocket experiences maximum dynamic pressure. Up until this point, the drag force on the rocket is quadrupling every time the speed is doubled. Beyond this point, the decreasing air density outweighs the increasing drag, and the forces on the rocket begin to relax. After max Q and 2 minutes and 30 seconds have passed, main engine cutoff and stage 1 separation occurs, revealing the stage 2 Merlin vacuum engine. This engine will take the payload to its final orbit in space. With no atmosphere creating the drag, this engine creates a mere 200,000 pounds of thrust and can burn for up to 400 seconds. The engine can be even restarted multiple times to deliver payloads to different orbits in one launch. After second stage burn is shut down, it's travelling at speeds of more than 27,000 kilometers an hour, flying parallel to the Earth's surface below, with altitude not dropping or increasing, meaning the vessel is successfully in orbit.
A modern method currently in its development stage is centrifugal launching systems. These are kinetic energy-based space launch systems that reduce dependency on traditional chemical rockets designed for launching 200 kilogram class satellites into low Earth orbit. The centrifuge is compiled of three main components. The vacuum chamber, nearly 100 meters in radius, kept at low pressure in order to allow high speeds and lower friction. The carbon fiber tether, a lightweight arm driven by the central electric drive, and finally the exit tunnel, where the satellite is released from. This contains vacuum doors which open and close as the satellite is released in order to decrease times between launch, as the chamber takes an hour and a half to reach launch pressure. The key benefits this method offers over traditional launch systems is a quarter of rocket fuel is required, there is an 1,000 reduction in total launch cost, and the speed allows for multiple launches per day. Commercial use of satellites is becoming more and more common as both cost and reliability improve with innovation. Spin launch offers the next step to vastly reduce cost and time prep. Spin launch also offers military applications. During 2004 in Iraq, 68% of munitions used were guided by satellites compared to only 10% in '91. This shows increasing dependency on technology and thus how important these innovations are. Finally, emergency communication. Due to low cost and short launch times, satellites can be launched quickly if major infrastructure is damaged. Elon Musk's Starlink has been utilised to provide Ukraine with internet services, crucial for civilians and military personnel. Although spin launch requires far less rocket fuel than a traditional launch, it still requires a rocket in order to put the satellite into the correct orbit. This does not completely remove the risks associated with a launch, only reduces them. Another issue is the extreme forces experienced during launch. A normal satellite launch experiences around 3 Gs of force, while spin launch over 10,000 G. This would destroy any current satellite, so Enterprise-class satellites that are compatible with kinetic launch without compromising cost, performance or mass must be designed and manufactured. Finally, this system involves fixed infrastructure like a traditional launch pad, so lacks the inherent mobility and flexibility of air launch alternatives.
Space elevator, space bridge, star ladder, and orbital lift. The idea behind is to connect a planet's surface with the space. This concept has been there for more than a century, but it was until the discovery of carbon nanotubes that it received serious attention. In the late 90s, NASA commissioned the first study about the space elevator and its feasibility. The space elevator would be an inexpensive and easy way to get payload into space. Without the elevator, the ideal cost will be the sum of the potential and kinetic energy costs in raising the payload from the surface of Earth to a geostationary orbit. Using the elevator, this cost reduces to just the kinetic energy. To avoid a fatal compressive strength, we can counterbalance the weight of the structure by pulling upwards. We can do this thanks to centrifugal forces. The structure will need to be located at the equator to work with Earth's rotation. If the elevator is not in sync with Earth's rotation, the tether will curve and break the elevator. The orbits will also need to be circular. To achieve that, we need centrifugal force to equal gravitational force. Centrifugal force is defined by the left side of the equation, while the force due to gravity is defined by the right side. For Earth, the radius will be of 42,186 kilometers. This is the distance from the center of the planet, so this will be about 36,000 kilometers above the surface of the planet at the equator. To avoid a shift in Earth's center of mass, we will need to extend the tether in both directions. A counterweight could be avoided using the same length in the upper half. To know what material could the tower be made of, we can calculate the max tension in the cable with this equation. This design will have to endure really high tensile stress, and we don't have any material capable of it. A tapered tower design will avoid the excessive stress, with a cross-section that varies with height in such a way that the tension in the tower remains uniform along its entire length and at the value that can be safely sustained by available construction materials. This requires the tapered tower to have a cross-section that increases exponentially with height up to the geostationary height and then decrease exponentially afterwards. For steel, the taper radio will be 3.53 times 10 to the 54 meters. For reference, the known universe is around 8.8 times 10 to the 26 meters. One future tech for space elevators are carbon nanotubes, reporting tensile strengths of 130 gigapascals, giving a taper radio of 1.6. Thank you very much.